All right, good. I'm glad someone's asking here about 44 or ones like it, because anything that has kind of this Archimedes principle, as I was trying to warn you when we were lecturing, is it's real easy to confuse whether we're talking about the fluid or the object that is in the fluid. And you'll see that in this problem, right? Let me read it here. It says, some fish have a density that is actually slightly less than the water, and therefore they must exert a force. That is, they must swim to stay submerged. So, going back to the lecture, we said anything with a density less than the fluid it's in. So, in the case of a fish that has a density less than seawater, or freshwater, depending on what kind of fish it is. But if it's less than that, it gets kind of pushed up to the top. And hopefully it's not too much less. In fact, that's kind of a death blow to a fish. When something goes wrong, I'll call them sick. But what ends up happening if they're sick and their body doesn't function right and they don't keep the density right, they could either kind of float to the top or sink to the bottom. And then they spend up so much energy and effort trying to swim down or swim up that then the sickness that they have gets worse, or they just die of exhaustion. But either way, they have problems. So that's can be a fatal blow to a fish. One little sickness can lead into a fatality, or if they try to stop it, then they end up. It's not maybe as dangerous if they sink to the bottom, but floating on the top, then they get vulnerable to other elements and prey. Anyways, I digress a little bit, but I'm going to start here then with this free body diagram and say, all right, let's take a look at a silly looking fish here. Maybe I should keep reading here. It says, what force must a 85 kilogram gupper exert to stay submerged in salt water if its body density is about 1,015? Okay. So keeping that in mind, I'm going to draw a picture here and say, okay, the fish is being pulled down because of its weight. It's being lifted up because of the Archimedes principle, the buoyant force. And according to this problem, this fish is also going to have to expel a little bit of effort, so I'll call it a force, and swim down. And that's the question, what force? So according to this free body diagram, if the fish is trying to just kind of stay at the same level, the forces up must equal the forces down, or kind of writing it like we did in chapters 4, 5, and 6, the sum of the forces in the vertical direction must then equal 0. All right, so in this case, I would say the buoyant force pushing it up minus the force swimming down minus gravity pulling it down has to be equal to 0. We're trying to solve this for the force of the fish swimming down, and it kind of makes sense then that it would be the buoyant force minus the weight. So the buoyant force, as it says, is a little greater than the weight. So the fish has to add a little more force to go down. So we've got to calculate both the buoyant force and the weight. And this is what I was saying. So let me just kind of change the order here, force equals. And I'll start with the buoyant force because, again, both of these can get confusing because one is the weight of the object, but the other is the weight of the displaced fluid. See, we learned from Archimedes that the buoyant force is equal to weight of the displaced fluid. So I'm going to put mg minus mg, but here's where I have to be careful. Weight is the weight of the fluid, and this is the weight of the object, which would be the fish, and the fluid would be the seawater, the salt water here. All right. Now, getting the weight of the object really isn't too much of a challenge. I'll just put minus because they directly say that the gupper is 85 kilograms. So I'll just go 85 times 9.8. But they don't really give me much information about the mass of the water that has been displaced by the fish. So I'm going to rearrange that using the concept of density. Maybe I'll put it up here. Remember, density is mass over volume. So I can replace mass with density times volume. But again, I need to be careful. Am I talking about the fish or the fluid? And of course, since this is supposed to be the mass of the fluid being displaced, we need the density of the fluid as well as the volume of the fluid. Okay. Well, again, let me kind of take advantage of the principle here, but realize that although this is the density of the fluid, I'm going to then say the density of the fluid that has been displaced for this case is also the same as the volume of the object, because the object, being this fish, is completely submerged. So notice then that I've kind of separated these two now. This is still the density of the fluid. And then technically this is still the volume of the fluid displaced, but I'm going to claim it's the same as the volume of the object. Because then I can replace volume with mass over density. Now that almost sounds like I'm working in circles, because if I think of this as, the volume of the fluid, then I would put mass of the fluid and density of the fluid. They'd cancel off, and I'm just back to here. But what I've done is really change this from the volume of the fluid to the volume of the object. So then I could say this is the mass of the object over the density of the object. And fortunately, they gave me that one, so that's why I was headed in that direction. And so they gave me these two, and I can look this one up here in the book, the chart that shows what is the density of the salt water. Okay, so I will look up the density of the salt water, and it looks like it says it is 1.025 kilograms per cubic meter. And then over here, I will put the 85 kilograms for the mass of the object. And then dividing by the density of the object. Oh, I forgot to put over here times 10 to the third. I just looked in the chart going, oh yeah, that's, all right, let me just move the decimal 3, put it right there. Okay, so this is 1,025 kilograms, okay. It dawned on me when I went to look here in the question about what's the density of the object, in this case the fish, they say it's 1,015. So you can see that the density of the fish is just a hair lower than the density of the fluid, and as a result, it's going to be slightly more of a buoyant force upward than a weight downward, which is why this problem says the fish has to make some kind of effort to swim downward. So all of this is going to give me the math to find out what is the force from the buoyancy. And then this is the force from its weights. Now I could do that in one shot, but I'm just kind of curious. So 1,025 here times 85 divided by 1,015 times 9.8. And so this would be 841.2 newtons from the buoyant force pushing up. And the weight of it is 833 newtons pulling it down. And so if we subtract the two, we're looking at an 8-point, I'll call it 2-1 newtons. And so just a little bit, which is good, just a very reasonable amount. And the same thing you kind of want to do when you're scuba diving is you have an air bladder that you can use your tank to fill up and change your buoyant force. And you try to get that balanced. You try to get the buoyant force lifting you up while you're diving to be about equal to your weight. And so the effort you spend swimming is kind of minimal. And that does a couple things. First of all, it doesn't tire you out, but more interesting is it doesn't make you consume a lot of oxygen, and therefore you don't run out of air in your tanks as you're down there diving. Okay, so that's kind of that important piece here. And of course, scuba diving, and even for fish, this needs to be adjustable. And so you guys in the life science probably kind of appreciate this and know how the fish can dissolve oxygens or other gases and play with its air bladder. When you're in a scuba environment, you just got a little button on your vest, and you just add some air or let some out. And again, especially as you're going down, the pressure builds up and that air bladder gets squeezed a little bit. And so you lose a buoyant force as you go down in pressure. And then, so if you go down a little bit, it squeezes it, kind of making you fall down the water column. And as long as you want to go down, that's not so bad, as long as you don't go too fast. But at some point, then, if you veer off your correct depth, you just kind of keep sinking until you realize, hey, I keep sinking, so you got to add some in. In fact, that happened to me not too long ago. I was following the top of a reef, and I visually, I would have sworn the reef was the same depth, but I looked later at my depth gauge and realized I was going down. I was thinking I was only at 40 feet, and I was moving along, and somewhere at about 50 feet, 55 feet, I was just, I just couldn't stay off the reef. I just kept kind of falling into the reef and crashing, and I realized, hey, wait a minute. I'm sinking here. I need to put a little air in my vest. So, I filled it up, and then I looked at my gauge. I'm going, oh, I'm at 55 feet. I go, and I looked around, and I kind of noticed now that I knew, but you couldn't really tell. The reef was just kind of long on a kind of a sloping bottom of the ocean, and so it was getting deeper on me. Anyways, I digress. So enjoy the problem. Take care.